Good morning, or maybe it's afternoon, or maybe it's evening. I don't know when you're watching this, but I'm at home this morning and I'm going to be talking to you about the force on a charged particle in an external field. I'm home with my family, so you may hear dogs barking or dishwasher running or my kids, Lena and Jonah, talking to me periodically, or me yelling at the cat. We'll see how this goes. But we need to start today just with a quick review of an electric field. And we know an electric field is set up around any charged object, and it is independent of a test charge. However, we do define an electric field in terms of a test charge. And so that definition is here. It is basically a force per unit charge. Newtons per coulomb is the unit for that. And this little guy down here is that little bitty test charge that does not influence the field that's set up by the charged object itself. So we've already talked about this. We did this yesterday in class. So here comes our new learning, and I am going a little out of order from the chapter. So we're going to now start talking about force on charged particles in an external field. So we're going to have a field set up by something, usually parallel plates. We're going to throw a charge in it, and we're going to see what happens. And we know from our work so far that if we put a charged particle in an electric field, it's going to experience a force. And so we're going to look at that today. But the next section in the textbook is that is in order is actually charged electric fields due to extended bodies, and we'll do that tomorrow. So I will make another video and we'll tackle that monster on a different day. Okay, so if we think about this kind of as the flip-flop of the definition of the electric field, this makes some hopefully good sense. We do have a few like caveats or physics fine print, as I like to call them. So we're going to make an assumption. We're going to assume that that charged particle that we're throwing in that external field is small in comparison to the charge that's setting up or creating the field. So kind of in your mind's eye, think about an electric field that is set up by a big charge or a line of charges or something that's got a lot of charge in it. And then we plop a little particle, a little charged particle, kind of like a test charge, in it. And it's going to experience a force. But we need that charge to be fairly small in comparison to the charge that is setting up the field. In physics, you are going to see a lot of times, you are going to see parallel plate capacitors. And we touched on parallel plate capacitors yesterday. And basically, parallel plate capacitors, they're used in all sorts of electronics. My guess is you've used them. If you've used capacitors in any of your electronics classes, this is what I'm talking about. So you're going to see here that I've got one plate here that's positively charged, and I've got another plate here that is negatively charged. And those field lines, should make sense, right, go from our positive plate to our negative plate. And if we take a charge here, and let's say we have it enter that field region with some initial velocity, and that initial velocity might be going like this way. And it experiences a force in that direction that is in line with the field, which is because that particle is positive. Remember, our electric field is defined in terms of a positive charged particle. Okay, so if we take a look over here at our equation, you're going to see it's basically the rearrangement of a definition of the electric field. So the force on a charged particle, that's this guy here, in a uniform, that word is important, uniform electric field, meaning it's evenly spaced, those lines are evenly spaced, it's set up, it's constant, hit, hit, nudge, nudge. That charge times the electric field is going to give us the force. All right, and the force has a positive direction. The force has a direction of the electric field if the charge is positive, right? Because the direction of the field is in terms of a positive test charge. If you throw a negative charge, the force on that charged object will be opposite. Okay. Excuse me. So at this point, we are ready to dive in and give it a shot. So we're going to be looking at example number 46, and number 46 is in on page 602. So go ahead and pause the video right now, take a moment and read the problem. Okay, so the first thing that I would suggest doing is drawing a picture and writing down your knowns. So right now, take a moment and do that. I know you're tempted to just continue on with the video, but you will get much more out of this experience if you pause and do what I ask you to do when I ask you to do it. So right now, pause the video, and I would like you to draw a picture of the situation. It may not look like mine when you're done, but you want to draw a picture of the situation and you want to list your knowns. Okay, so here is my picture of the situation, and those black lines here are telling us or showing us what the direction of the electric field is. And I have my charged particle here, which is an electron, so it has a negative charge with a velocity that is along the field line. So you'll notice that that velocity is hanging out or in the same direction as the electric field. And I did have to go to my indices in the very back. We got some physical constants. We also have some like physical properties in the very back part of my book. Or the very front page, it's somewhere. You also have these in your AP equation sheet, but you'll need the mass of an electron and then this elementary charge you'll need as well. Once we have our knowns set up, we need to ask ourselves what's happening here. Like, our charged particle is in an electric field. Is that charged particle going to experience force? The answer to that question is yes. What direction is that going to be? So right now, I'd like you to take a moment and I'd like you to draw the direction of that force that's acting on that charged particle. So go ahead and pause your video and do that. All right, so I'm going to draw the force that's going to act on this particle. And because this is an electron, it is going to experience a force in the opposite direction of my field, right? So I'm going to write this here, that this is my force. And we know that that force is going to be proportional to the size of the electric field and then the charge on the particle, which we have both of those things, right? This is our charge on our particle. That little E is our fundamental charge on an electron. And then here's our electric field. So if we read the problem, it's really going to read a whole lot like a kinematics problem. And you should be thinking that, right? You'd be like, hey, wait a minute. That sounds a lot like how long does it take for something to come to a stop? Yep, we're going to be using our kinematics equations. Now, notice that our field here is uniform. What does that tell us about our acceleration? It tells us that our acceleration is going to be constant. So therefore, we're going to be able to use our constant acceleration equations. You with me so far? But before we do that, we're going to need to use our force information in order to find the acceleration. So our first tactic is to use our force information to find our acceleration of our object. So we're going to go back to good old draw a diagram and sum your forces, right? Looks like a force diagram right here if I ever saw one. All right, so we got our force diagram, and we're going to set our F is equal to ma, and we know our force is going to be in the negative direction, and from our previous discussion, we know that it's going to be equal to the charge on the electron multiplied by the electric field. All right, so there we are. Now notice I've got a negative in front of that, noting that the force is to the left. So once we solve that out, go ahead and pause the video right now. And I'd like you to solve for your acceleration, get a value for your acceleration. Okay, so once I've rearranged, here is my acceleration as really, 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 really big. Do you notice how huge that is? Look at that. Humongous, huge, tiny Elvis. And it's going to be really large because that mass in the electron is so very small. So if you look in the denominator of that equation, that's times 10 to the negative 31st power. That's itty bitty teeny weeny, right? Really, really small. Okay, so now once we are at this point, all of our new learning is over, right? We've applied our information about an electric field acting on a charged particle. Now, all you got to do is use your kinematics equations. Now, again, we know we can use our constant acceleration kinematics equations because that field was uniform. Therefore, that charged particle will experience a constant force in that electric field. I cannot stress that enough. This only works when you have a uniform field. Okay, so you can go ahead and use your kinematics equation. So pause right now, and I want you to finish part A and part B using your kinematics equations. When you're finished with that, then come back to the video and check your work. All right, so you're back with me finishing your problem on your own. So you can see the equation that I've chosen to use. You could have done B, then done A, like you could have flipped-flopped those, but regardless, we should have found the displacement as 7.12 centimeters, or 7.12 times 10 to the negative 2 meters. And the time it takes to come to a stop has really small, which makes sense because that acceleration was huge, right? That acceleration is huge. And don't be alarmed when you get accelerations for objects that are charged particles that are really large. That's okay. It's when you have velocities that are outside the or more than the speed of light that you have a problem. We're not going to worry about that. Oh, that's my daughter Lena. Say hi, Lena.
Hi.
You're going to have to wait for the yellow yarn. Do you want to say hi, Jonah? Jonah doesn't want to say hi, but I bet he'll use his fart gun for you. Anyway, so that's it for today's installment, and we are going to give you an assignment. Your assignment I'll have on Canvas as well, but it is finishing the section of force on particle in a field. You already had the assignment of question 1 and problem 39. You also need to do problem 32. Sorry, 42, 47, and 50. All right, good luck. Give me a text if you need help.